Okay. Okay, guys. Let's before going to talk about chapter 2 and start chapter 2, I'm going to review an additional topic, which is not for chapter 1, but it's necessary for fluid mechanics, which is Reynolds number. So I wrote the meaning of Reynolds number here, and what is exactly defined, not based on equation, based on the forces, which is the ratio of inertial forces to viscous forces. So let's go for understanding the meaning of inertial force in rigid body motion. Inertia means is resistance of any physical object to a change of in its velocity. So velocity change can be done by speed or by the direction of velocity. And inertia means that how much a rigid body doesn't want or want to keep its constant velocity in terms of direction or speed. The inertial force, as you know from the dynamics, is in direct proportion with mass and velocity. So the more mass is going to be momentum, and it can be defined in m times v, mass times velocity. So it's going to be a direct proportion of mass and velocity. But in the fluid mechanics, so velocity is again velocity, but fluid mass or heaviness of the fluid characterized by velocity, by density, so which is rho. Just keep that in one part. And let's go for viscous force. The viscous force, as we talked about in the previous session, that is the fluidity of fluids. So like honey has higher viscosity, means that less fluidity, right? So as I wrote it here, two layers of the fluid, the more viscous forces, which is the more shear stress or the more viscosity, means that the more friction between the layers you will see. And these two forces, viscous force and inertial force, are against each other. So you can see this one as in rigid body motion is the friction. Here is the friction between layers. For example, if you have two layers, V1 and V2, that these two are different, then, for example, V1 is higher than V2, right? So the below layer wants to stop the top layer from moving. They want to move to each other because of the friction. If you have two layers with the same velocity, that's going to be different. Why? Because these two are stick together and move together. That's exactly what happens when you have a fluid close to a constant plate or a plate that is not moving or is at rest. Then fluid stick to the surface and you have nothing like force between two material, the fluid and the plate. And also in top plate, when you have two layers of fluid that move together, or one of those are pulled, then the layer of fluid that is close to that, because of no slip boundary conditions, we can stick to that layer. So it's very important to know that these two forces are the main forces in fluid mechanics, that it depends on how much these two are different. And Reynolds number is a non-unit or unitless parameter that defines how much is the ratio between these two. So it's defined based on inertial forces and viscous forces. You can see the rho times L. Rho is the density. L is a characteristic length and depends to the shape of the channel or the shape of the shape factor. It's like a shape factor that fluid passes through it. For example, in a pipe, it's like diameter of the pipe. It also can be defined as the characteristic length or the characteristic diameter could be defined as 4AS over P. That's the perimeter of the channel. Or for example, for a pipe, 4 times L AS pi R squared over 2 pi R, right? So R is going to be cancelled with I, pi with pi, and this is going to be 2R or diameter. So if you multiply the characteristic length times the rho, absolutely characteristic length has a unit of meter, but it shows that you already have a meaning of the volume time density. So it gives you almost mass. Velocity gives you mass time velocity, gives you meaning from inertial forces. And viscous forces, it depends to the mu. So it, as you can see, you can prove that how the Reynolds number calculated, but it's not for you. You cannot do it right now. You have to maybe in the chapter 9, when we are talking about chapter 8, that we are talking about the pipe flow, but not right now. I wrote how it gives you the non-unit number. What is the point for calculating the Reynolds number is define and understand the flow is laminar or turbulent. So again, we will talk about that later, but to give you an understanding, physical understanding about that, the laminar flow, the layers are passed over each other smoothly, right? These are like streamlines or a flow that are moving through a channel. But in turbulent flow, these are like mostly turning here, okay? When the Reynolds number is very high, and we'll talk about that, what does it mean, a high number? We don't know right now, but we will talk about it. When the Reynolds number is high, you will have a turbulent flow. Let's have a physical understanding. When the Reynolds number is high, means that the viscous forces are high. So inertial forces are less. It means that you have a frictional force between two layers. So it shows that you have two, if you have considered 3 layers here, the top layer is going to turn this fluid box, which is here. The below one going to give you viscous force in this way, and the top layer going to give you another force here, because this layer going to give the top layer a force of F tau in this way. And based on the Newton's law, you have another force in this direction. Then you have two forces that give you a clockwise rotation on this box of fluid, right? At the same time, you have inertial force that is based on that the box of this fluid wants to move and keep it moving. When this one is low and the friction force is high, wants to rotate. That's why you have mixing here. The more Reynolds number you have means that the more clockwise rotation here you have, and the less envy you have here. That's why you have more mixing and more rotation. That's the meaning of Reynolds number. Right. Are you in the class?
I'm in the classroom. We have a couple.
No, that's a temporary class for me. Because yeah, the other classes doesn't work, the document camera. So I came here maybe for just 2 sessions, then new class assigned.
Do you know what time?
I'm out 10:15.
Okay.
Thank you so much. That's the general sum. So anyone has question to ask? You can unmute yourself and ask if you want. No? Okay, let's go. Let's go and solve question. That's the example that you need for maybe your homework. It helps you to solve the questions and one of the questions. And then we will move to chapter 2. So here is an example. How the profile, the velocity profile works, and how you have to calculate tau and the shear force between the fluid and a body. So consider that you have a cube, that the mass is 2 kilograms, and you have a shape like this as is coming down. But between these two, you have SAE10 oil at 20 degrees. And the mu of that is given. So the cube slides down, and theta is 10 degrees. Okay? But it gives you one important thing here. The velocity is constant. Velocity is constant means you don't have any acceleration. It asks you to calculate the S speed of cube. What is U? And also give you the H, the thickness of SA10 or lubrication. Let's go for writing the given. One is H, which is 10 to the power of -3. Then is mass, 2 kilogram. Third part is theta, degree, and also mu is given. Mu of oil is 0.104 newtons second per meter cube. What else is given? Oh, it has to give you, yeah, side of the cube, which is A. I forgot, yeah, it's here, 10 centimeter, so 0.1 meter. So these are the given. Okay. At first, we wrote the free body diagram. In X direction, it mentioned that there is no acceleration, right? When there is no acceleration, then we can see that sigma F in X direction is MA, it has to be 0 because the acceleration is 0. Okay, so it means constant velocity. Perfect. The second thing I'm going to talk is how we find what is the angle here. This angle is theta. But how I can find it? In mathematics, when you have two arbitrary lines like this, and angle is theta, and two other sides like this. But this way, it has to be this. If one of the sides of the angle is perpendicular to one of the other sides of the other angle, and this side also perpendicular to that, the angle between these two sides are equal. So when you see here, y direction is normal, we define or reference as a normal side of the plate that the cube is coming down. And mg direction is perpendicular to or Earth, right? So this is perpendicular here, and or reference line in y direction is perpendicular here. Then we can say that the angle here is theta. Okay. So here is the force of mg, and that's it. So if we put the name here as F2 and this one as F1, is it right to write that F1 is mg sine of theta and F2 is mg cosine of theta? What else we need? The other thing that we need is F tau. This that stops the cube to comes down. That's our friction force. So sigma of x equal to 0, right? It means that F tau, which is negative direction, plus F1 is equal to 0. What is F tau? F tau is shear stress times the area, correct? What is the area? If that's a cube, then that's the area here should be constant, right? The area is pi to the power of 2. What about tau? Mu du or dy, or mu u over h. Why u over h? Because it's mentioned here. Velocity distribution or profile is linear. Here also shows the, so based on our calculation and the profile equation distribution that we talk about in chapter 1, then you can write that mu u over H is our shear stress. Then combination of these two, F tau is mu A squared U over H. And based on this, F1 is equal to F tau. So this one should be equal to mg sine of theta. Okay. So what asks us to calculate? You keep U on one side and the rest of known parameters and terms the other side. So U is equal to mg sine theta times H over mu A squared. If you plug in the terms, then final answer U is 3.27 meter per second. I think that this is the hardest question that may ask you before for the linear distribution of the profile, but nonlinear is also possible because that's not always linear distribution, especially for the pipes. But for now, that's enough for you to, for chapter one is really enough. So most of the questions, by understanding this month, you can solve most of the questions in the book and homeworks. Any question till now?
Yes, I have a question.
Yep.
Will any Newtonic fluid have a linear shear profile like we just saw?
In reality?
Yes.
Hmm.
Is that what decides the profile? What decides the shear profile being linear?
If you're asking about this profile, the real profile is like one of these are moving, this one is in constant velocity, right? Or at rest. Then this is the distribution of the profile, right? And it's linear. In reality, maybe it's not. But one of the main things that we have to consider here is the edge. If edge is very small in terms of millimeter, maybe 1 millimeter or close to that, then the change, the nonlinear form of this is very small, and you can assume that it's linear. Has answered your question or no?
Yes, thank you.
But yeah, in reality, no. You don't have a linear, really linear profile in reality, never. And but again, if you are coming to this major, fluid mechanics, remember that fluid mechanics is full of assumptions that at first none of those make sense. Yeah, you're right. In reality, we don't have a linear, pure linear profile, but it works. You have to know that that's like art. You have to use assumptions, and finally, it's gonna work. Any other question? Okay, we can move forward. Chapter 2, fluid statics. One of those is pressure. Most important thing in this chapter is the pressure in fluid when it's at rest. And what is the pressure? It indicates normal force per unit area. But acting on a point. Okay, so if you write the equation, the force is equal to pressure times area. So F is P pressure times A. So F is equal to P times A. So I have a question for you. Is the force a vector or not? As you see, I wrote a vector shape on top of it because the force has the magnitude and direction. So force is a vector, but pressure is a scalar. It means that area should be a vector. Why? Because scalar multiplied by vector gives a vector. If you have two scalar, no. Two scalar multiply two scalars, the answer would be a scalar, not a vector. So it means the only option that we have is area. But what you think that area doesn't have any direction? Yeah, it has. Direction is the normal of the surface. So any surface, like the surface, it has a normal direction, normal to the surface. From any surface in 3D, you can pass one line that is normal to the surface, but you can pass infinity number of the lines here, 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 here. At any point, you can pass one line, but it has a center of the mass or center of the shape. That's the point of pressure because of the force passing through it. So the also normal vector also pass through that point. If you have only one point, then you have a unique line, which is normal that to this surface, but pass through the CM or center of the mass or center of the shape. It depends that you has a mass on it. So I wrote it here for you that this is normal vector of the plane. Okay. So what's the point of assuming a fluid moves through a shape like this? So that's the way we can prove Pascal's law, that pressure at a point in a fluid at rest is independent of the direction if there are no shearing stresses. So we'll talk about them. But let's say we have a infinitesimal volume, but with arbitrary shape. Keep these two lines, but with the angle of theta that we don't know what's that, so it's arbitrary. But Only thing that we know that the volume of that is moving or limit to 0. That's the main assumption here. Okay. And to write it down, the gamma fluid, gamma is the fluid specific weight. Specific weight. And we assume that as a rigid body, no relative motion between the fluid. So what does it mean? No relation, no relative motion between within the fluid means between the layers. So no relative motion means that you consider that no shearing stresses. That's also an assumption. Why? Because of no relative motion. What is the second assumption? Is the volume, infinitesimal volume amount. What's the volume? Volume is delta x, delta y, delta z. Delta z times delta x times delta y is actually give you the volume of the whole cube, but it's half of it. So it has to be over 2. That's a delta v. Here also we have it. That's the weight of it. The weight of a volume box is the volume times rho g, right? The gamma is rho g. Okay. What else we have? It given you here or not, but we have also A, because everything is arbitrary. We don't want to, the only thing that we assume that there is no relative motion between the layers and no shearing stresses. And why? Because we don't want to have a rotation here on this volume. So we have A, which is in X direction, consider 0, A, Y, and A, Z. Okay. What's the area in this side? AY. Why I wrote it AY? Because the normal direction to the plane here is Y direction. So we wrote it AY. And is equal to what? Delta X, delta Z. Right? What about this surface? Is a Z because of the normal direction. That's the amount. Delta X, delta Y. I guess you can see it better, right? And that's AS. AS is delta S times delta X. Okay, so what do we want to do? Outside that we had sigma Y. In Y direction, we want to write what is the summation of the forces. At first, we have Py, which is here, 1 force in positive Y direction. So Py, pressure at this side, times delta X times delta Z, minus first PS, times delta X delta S, but in this direction, in Y direction. So it's should be multiplied by sine of theta because you want to have this force. Sine of theta is equal to m at a y. Ay. In y direction, in z direction, also you have same but with different subscription. P and z direction times delta x delta y, which is here. Minus ps times delta x delta s, but in z direction, cosine of theta, and we don't want, just we are going to consider the surface first. So for now, we don't want to consider mg, which is a body force. So yeah, just these are just the acceleration because of the surface forces is equal to mz, az. Okay. Now I'll put number 1 here. Number 2 is delta s cosine of theta. If that's delta s times cosine of theta gives you delta y, right? If you multiply delta s in cosine of theta, gives you this line from here to here. So this is going to be delta y, and delta s sine of theta is give you this delta z, which gives you this line. Okay, and I can replace the mass with rho delta x delta y delta z over 2, which is the volume, right? If I use 1 plug in, 2 in 1, then what I have first P y delta x delta y minus, instead of P s, we have to keep it, but we can rewrite delta s sine of theta with delta z. So Ps delta x delta z, right, is equal to, replace m with rho delta x delta y delta z over 2, and multiply that by a y. And here, for the second one in z direction, we have pz delta x delta y minus ps delta x delta y. Why? Because we have delta s cosine of theta, and the delta s cosine of theta is equal to delta y. Should be equal to rho delta x delta y delta z over 2 multiplied by AC. Okay. Let's cancel out delta x delta y. I'm sorry. Let's just cancel out delta. Oh, that's delta z. First one is delta. Sorry. Okay. And delta x delta y, delta x delta z. Delta x delta z are going to be canceled out from each side. Delta x delta y also cancel out here. But based on our assumption, delta v goes to 0, right? If delta z or delta v goes to 0 from here, it means that delta x, delta y, and delta z each goes to 0. So delta y goes to 0 here delta Z also goes to 0, right? Means that this term totally, these two terms going to 0. What's the result? Py is equal to Ps, Pz is equal to Ps, right? Py, Pz, and Ps are equal. Interesting. That's the Pascal's law. We'll write it here. Pascal's law is about pressure at a point. Pressure at a point, fluid mechanics in a fluid at rest or no motion is independent of direction if no shearing stresses That's the Pascal's law. It's maybe for you, it's just a simple thing, but is base assumption in most of the fluid equation. Why? Because we are giving, as you remember, we are talking about the volume, that any parameter in fluid mechanics is based on the average, right? Averaging over volume. So you're not talking about the molecules here. You're talking about a volume. When you're talking about volume or not individual molecules, then you're getting an average of temperature, average of the velocity, average. But when you give a volume to this shape, you cannot say that, okay, we have one pressure here. Why? Because in a fluid, you have two pressures, one pressure here, and different pressures, right? So that means that you cannot consider that pressure is a constant here, right? The Pascal's law is based on that assumption that the volume moves to 0. That gives you that this understanding and proven that the fluid at rest, pressure at the point, is independent of direction, means that is a scale, right? In rigid body, you have this information because that's a rigid body, right? But we should prove it in fluid mechanics as well. So when we prove that for in fluid mechanics, now when we can remember that why we mentioned that the rigid body motion, solid mechanics, and fluid mechanics based on the volume, on infinitesimal volume, are the same. So approaches are the same, but based on this type of proof, like Pascal's law. So we need it. Maybe you don't need to prove it all the time, but yes, we need it. Any question till now? Okay. Okay, let's talk about pressure field. Okay, so you have a volume, box of volume here. Okay, that's your y direction. Okay, and you have very small size of box. Then if you have pressure here, And also the other side has very small change in the pressure. So what we are going to do here, we are going to say that what is the pressure in absence of shear stress, again, because also we consider that flow is at rest, how the pressure varies from point to point. That gives you the pressure field. So first, the flow is at rest, or there is no shear stress. And these are the pressures in each side, okay? So if you write the sigma in, it just didn't show the x direction, but x and y direction are the same. Okay, so one of those should be just proved. Only thing that matters is in z direction because you have the weight. Okay. So if you remember, here we mentioned that one of the assumptions is that we don't consider the volume or body force, right? That's why the pressures are independent of the size. But now we have to consider, because you cannot just say that the volume is not, doesn't matter, and there is no body force here. So we have it. That's why we need to use it and prove the pressure distribution or pressure field. Okay. So this is the body force. Now we are going to consider that right now. Okay. So in y direction, what we have? We have one pressure here, 1/4, that's pressure times area is force, and force in y direction. Okay. Can I say that the P times delta x delta z can be canceled out with this P times delta x delta z, right? The only thing that I have, because that's in negative direction, is minus derivative of Py dy delta x delta z. I can write everything as a delta or d. So dx, dy, dd. Okay. In z direction, in x direction are the same. So rewrite it again. In z are the same. From p of x, dx, dy, dz. What about the z? In z direction, you have also cancel out these two. Then you have p over z, dx, dy, dz. These are only forces for pressure. Okay. So as a surface forces. So delta in F, but in surface forces, you have delta of Fx, I, that's number, scalar, plus delta of Y, J, plus, yes, plus delta of Z, K. Okay? So I brought negative here from all terms, X, I, plus Y, plus B, or V of delta X, delta Y, delta Z. I can write that this is delta V of volume, right? And I can replace this one with the gradient of the P. Gradient of the P is gradient in mathematics. Absolutely, you have to review it again if you don't remember. But gradient of a parameter like scalar is derivative of that scalar versus x plus derivative versus y plus derivative versus z. That's the gradient. Okay. And also it's a vector, so it has to have direction. Okay. It has I, J, and K. Okay. So here as a final answer, delta F in S is equal to minus gradient of the P times delta V. That's a scalar, and that's the vector. Okay. But now we are going to consider the delta W, which is the volume of or the weight of or flux of fluid, right? And then finally we can write that the true acceleration of this volume now can say that it's a rigid body, right? Is equal to surface forces plus body forces. The surface force, we have it, we prove it, that is gradient of the P times delta V, that's the volume. And what is the W? The W is the rho G times volume, gamma delta V in K direction, right? Again, if you have K here, means that you have direction. Then you have to remember that this is also as direction because that's a vector. Delta V is not a vector. Delta V is not a vector. Delta V is not a vector. But acceleration, the K direction, and gradient of the P are the directions. Okay. So in the form, you can say that sigma F is equal to rho times A, it canceling out the volumes, is equal to what? Minus gradient of the P minus gamma in K. Okay? That's the general equation of the motion. Any question till now? Okay. So that's the general equation of the motion. So you have acceleration and the fluid moves, right? But now pressure variation when the fluid is at rest, and means that A is equal to 0. Then you can write that, okay, you don't have the other term, then that's the general equation, right? So the gradient of the P times plus gamma K should be 0, okay? So let's rewrite it here. Equal to 0 because the only thing that we have for I direction is that. Y direction is also 0. But in K direction is equal to minus gamma. Okay? Shows that if the fluid is at rest, the pressure is only function of Z and does not depend on X and Y direction. Okay. So only Z. Why? Because we have the weight of the fluid, right? So if we are going to find the delta P here, for example, P2, that these 2 points have a different depth, the P2 and P1, absolutely point by point is going to change, right? Absolutely linear. So the pressure here, if it's high, then here this is low and this is higher, but linearly is going to change, okay? So we'll get the integral of that to find the pressure difference. But the other side also should find the integral of the other side, which is from Z2 and Zy. The only thing that matters is depth. So from Z1 to Z2, and the only thing that we have here is a K direction, right? Because that's in K direction. So the K direction means dz. Getting the integral of that, gamma Z2 minus Z1 is the answer. In other form, delta P is rho minus rho EH. Okay? That's the only equation that you need when the fluid is at rest. One other thing that we have to talk about is this sign. When you have this sign, means that this is the free surface. Free surface means atmospheric pressure. The atmosphere, and it is for reference. Pressure. So any pressure here in total is the pressure of the point plus the pressure of the atmosphere. But since the atmospheric pressure is everywhere, then we can say that, okay, P atmosphere is 0 because it's our reference number, that we are talking about only the pressures of the gauge pressure, because everything is based on relative to the atmospheric pressure, right? So that's a reference here that, okay, here is that pressure of reference for P0, okay? Or we show that P atmosphere, but you can assume that it's 0 Pascal. Depends that one's total pressure or not. Always remember a point here. Most of the students, I saw that they have problem. Always remember, in a fluid, at rest, when you're moving, and you are moving, moving upward, the pressure decreases. So here, you can write that P2 is smaller than P1. And what else you have to know about the pressure variation in hydrostatic distribution? Hydrostatic means that hydro gives you the meaning of the fluid. Static means that is at rest. Fluid is incompressible and only is a function of depth. So what's the meaning of, what's the first example? You have different shapes, right? And the volume of the fluid that you have in this, that in each of these bottles are different, but it doesn't matter. If this is 0.1, if this is 0.2, 0.3, or maybe 0.4, 1, 2, 3, 4. All these pressure that are at the same depth versus the atmospheric reference, which is here, have the same pressure. Okay, that's the first rule that you have to remember. The second thing is that when two fluids that cannot be mixed, like gasoline and water, when they are in close contact, but in equilibrium state, the pressure at the point in interface is the same. So P, if that's the point is 1, P1 of gasoline is equal to P1 of water. This is also important. So it doesn't matter you are moving to calculate pressure at one from upside or downside, these two should give you the same number, because the pressure at this point only depends on the depth, not the fluid, the type of fluid that is at the top of it. So if you change the gasoline, bring the gasoline here and water on top, you absolutely change. But again, why change? Because the amount, that's the gum of the water or the gum of gasoline are different. But this pressure is absolutely different in the second type. But if you calculate from the gasoline direction or the water direction, these two are the same. The other thing is that standard atmosphere, also you need that for question 1 of the homework. This is also available in table 2.1. The other thing is the absolute pressure and gauge pressure. We already talked about it in the previous chapter and now here, that since the atmospheric pressure is everywhere, the main pressure or the total pressure is absolute pressure. But absolute pressure is when atmospheric pressure is also considered. So P absolute is measured related to a perfect vacuum. Perfect vacuum means that the atmospheric pressure is also added. So P absolute is P of gauge plus P atmospheric. Okay, so these two are summed together, sum up. Why? Because we are getting relative to the vacuum pressure. But if we move to find only because we are living on Earth, atmospheric pressure is everywhere. So we don't want to all the time add that atmospheric of atmosphere everywhere added to or pressure. So why only just consider peak gauge, which is Pg, right? The gauge pressure, which is relative to the atmospheric pressure. So it's going to be P absolute minus P atmospheric. That's the other thing that you need. Any question till now? Okay. Two six manometry. Okay. Different type of manometer are shown here, but the simplest one the simplest type of manometer is piezometer, right? The piezometer doesn't, it has only a container here and a fluid, all the same type, and then a vertical tube, okay? So the container has a pressure here, okay? And you have an open top, open at top that is the atmospheric pressure, right? Okay, so what it shows is that how much the fluid is going to go upward, okay? It means that you have a pressure of in this container, then it creates a force here that push the water or any fluid that you have here upward. If you get the gamma h or rho gh of these from these 2 points, it means that if you calculate the gauge pressure here, or plus atmospheric pressure gives you how much is the pressure here. So that's the point of how using the manometer to calculate the pressure or measure the pressure at measure the pressure at the container. Okay. Now I have a question here for you to remember. If that's point A and that's point B, which one is higher? P A is higher than P B. Why? Because if you are moving from point B to A, you have to go downward. So it has more depth, then that's higher. Okay. This is also you have to remember. But now we are going to calculate how much is the A. Okay. Sometimes you have more complex type of the shapes. So I will give you 4 steps that works for me to answer any type of manometer or piezometer or YouTube manometer, and it all the time works. So first, pick a point. Second, try to escape. Third, when you are going upward, use negative now sign, and downward, positive. And 4, did you escape? If yes, then minus P atmosphere, or better to write P end, equal to, okay? What does, first, pick a point. I choose point A. Try to escape. Escape from this container, going here and going top, right? And I reach here. So first point is PA, okay? Then I'm moving from this point to this point. These two are the same line, nothing changed, okay? Then I'm moving from this point to point B. I'm going upward, yes, negative. What's the amount of it? Is gamma water times H1. Did you escape? Yes. When you're at the end, P of the end, which is atmospheric pressure equal to 0. That's a general equation. So now you want to find what is the pressure at A. Pressure at A is gamma water H1 plus P atmosphere. It always works, okay? But before moving to this part and use these 4 steps, let's talk about disadvantage of the simplest type of manometer or piezometer. The main disadvantage is it's only useful when the container pressure is higher than pressure at atmospheric pressure. Why? Because if the atmospheric pressure is higher, then the pressure here is not that much to push uh, the fluid upward. It's coming back, right? So there is not any edge for you to measure and then find uh, what is the pressure difference between the container and the atmospheric pressure. So to solve that, we use the YouTube manometer. So what is the advantage of this? The first advantage is one, the fluid at container could be fluid or gas, right? Here you cannot have a gas, but here, if you put a fluid here, then you can have a gas here. So this is going to be, it's possible to be a gas or liquid, right? Any type of fluid. That's the first, is the advantage of this one. The fluid at container could be liquid or gas, or absolutely liquid could be, but could be gas. Second is the gauge pressure at A can be determined anyway, with PA higher than P atmospheric pressure, or is lower than atmospheric. The third advantage of that is two, if you have two containers here, see? If you have two containers, both of them are gas, you can calculate the pressure difference. So it can be used to measure the pressure difference in two containers. A and okay. So based on these three advantages, most of the time you see the YouTube manometers in yeah, the time is up, but let me finish this one, and maybe next time we'll talk about more examples. Maybe I just posted the end of this part for you guys, but that's easy. But we have to talk about the inclined tube manometer next time. So that's only example. Let's use these 4 steps. Let's see how it works. Point A. PA is selected. Then try to escape. This line is going to be your line for escaping. Then moving to point A. Nothing changed because these two are the same line. Going to point 2. Minus is positive because going downward. What is the gamma? Is gamma 1, and H1 is the amount, right? You don't know what is this H. Let's put it H star, okay? You're going down and the gamma is gamma 2 plus gamma 2 H star. You're here. Let's move on the other side, right? Nothing changed, but then you're going to move here. This is also H star. You're going to upward minus gamma H star. Then from this point, you are moving here to escape. So from point 3 here, you have gamma 2, again negative gamma 2 H2. You escape? Yes. So minus P atmosphere equal to 0. Whenever you don't know what is the H star, these two for sure going to be canceled out. Or you can jump from this point here because you know the answer would be the same. Then PA minus P atmosphere or P gauge at A is equal to gamma 2H2 minus gamma 1. I bring these to the others. Yes, we have to stop here today. I will try best to reach our daily plan. We have to move forward a little more faster. Thank you so much, guys. Do you have any questions?
No, thank you.
Okay.
No, thank you.
Have a good one, guys.